There are many applications of queuing system. We are going to discuss the abstract queuing system in the further lecture. The easiest or the simplest queuing model, that is a Markovian queuing model, that is MM1 queuing model. Later we are going to relate with the birth-death process also. In the MM1 queuing model, the inter-arrival time is exponentially distributed. As I discussed the Poisson process in the previous lecture, whenever you have a arrival follows a Poisson process, then the inter-arrival time follows a exponential distribution and are independent also. So, here the first information is a arrival process follows a Poisson process with the intensity or rate lambda. That means the inter-arrival times are independent and each one is exponentially distributed with the parameter lambda. The second information, that is service time. Service times are exponentially distributed with the parameter mu, and the service times are independent for each customers, and that is also independent with the arrival process. That means there is no dependency over the arrival pattern with the service pattern. Service times and the inter-arrival times are independent. Then the third information, only one server in the system. That is a queuing system in which only one server, and the fourth information is missing. That means it is a default, it is a infinite capacity model. Infinite capacity model. Now our interest is to find out the behavior of a queuing system or the behavior of number of customers in the system at any time t. Therefore, you can define a random variable n of t, that is nothing but the number of customers in the system at time t. Therefore, this is going to form a stochastic process over the t. Since the inter-arrival time is exponentially distributed and the service times are exponentially distributed, the memoryless property is going to be satisfied throughout all the time. Therefore, this stochastic process, there is a discrete state continuous time stochastic process satisfying the Markov property. Therefore, this is a Markov process. Since inter-arrival time is exponentially distributed and the service time is exponentially distributed and both are independent and the service time is also independent for each customers. Therefore, this stochastic process satisfies the memoryless property at all time points. Therefore, this discrete state, because the possible values of n of t, since it is a number of customers, the possible values are 0, 1, 2 and so on, countably infinite. Therefore, it is a discrete state and you are observing the system over the time. Therefore, it is a continuous time. Therefore, this stochastic process is a discrete state continuous time stochastic process satisfying the Markov property based on these assumptions. Therefore, n of t is a Markov process. Since the state space is a discrete, therefore, this is a Markov chain. Therefore, this is a continuous time Markov chain. Therefore, n of t is a CTMC. So, one can write the state transition diagram for this CTMC. That means the possible states are 0, 1, 2 and so on. So, this will form a nodes and you try to find out what is the rate in which the system is moving from one state to other state. Since it is a MM1 queuing model, therefore, whenever the system is in the state 0, by the inter-arrival time which is exponentially distributed, the number of customers in the system will be incremented by 1. Therefore, that rate will be lambda, or the system moving from the state 0 to 1, it spends exponentially distributed amount of time here before moving into the state 1. Once the system come to the state 1, either one more arrival is possible, or the customer who is under service, then service could have been finished. Therefore, the service time is exponentially distributed with the parameter mu. Therefore, the system goes from the state 1 to 0 with the parameter mu. Similarly, from 1 to 2, because of the inter-arrival time is exponentially distributed with the parameter lambda, therefore, this is lambda. Since the arrival follows a Poisson process, in a very small interval of time, only one customer is possible with the probability lambda times delta t and so on. Therefore, there is no way the system goes from one state to jump into more than one state. That is not possible forward. So, only one step forward is possible because of the arrival process follows a Poisson process, and since we have only one servers in the system also decremented by only one level below. Therefore, this is going to form a birth-death process. The reason for this CTMC going to be a birth-death process, because of the arrival process follows a Poisson process. So, whatever the assumptions we have it for the Poisson process, that is going to be satisfied. And since we have only one server in the system and he does the service for only one customer at a time, after finishing that server, after finishing the customer's service, then it move into the next service immediately and so on if the customers are available in the queue. Therefore, the system goes to the one state below by only one move only. It won't move from 2 to 0 or 3 to 1 and so on. Therefore, this CTMC is a birth-death process. Therefore, I am connecting the CTMC with the MM1 queue, in particular the CTMC with the birth-death process. Because of the transitions due to arrival or the departure of a customer, and only nearest neighbors transitions are allowed because of the assumptions which we have made. Therefore, this is going to be a continuous time Markov chain with the rate in which the system moves from the state I to I plus 1, that rate is lambda, and the system moves from the state I to I minus 1, that rate is mu, and all other rates are going to be 0 other than the diagonal element, and these rates also constant, not state dependent rates. Therefore, this is a birth-death process with the birth rates lambda and the death rates mu. So, this is a sample path. Suppose at time 0 one customer in the system, then service is over, then the second customer enter into the system. Now, the number of customers in the system is 1 and so on. So, that means that this duration is the service time for the first customer, and from this point to this point, that is the inter-arrival time of the second customer entering into the system, and from this time point to this time point, that is the service time for the second customer, which is independent of the service time for the first customer, and this is the time point second customer enter, and this is a time point in which the third customer enters. Therefore, the inter-arrival time is from this point to this point and so on. So, this is the dynamics of a number of customers in the system over the time. Therefore, this stochastic process is a discrete state continuous time stochastic process satisfying the Markov property. Therefore, this is a continuous time Markov chain. So, later I am going to simulate the MM1 queuing model using some simulation technique. So, the conclusion is the underlying stochastic process for the MM1 queuing model is a birth-death process. The N of t is a stochastic process. So, this stochastic process is a birth-death process. Therefore, now we are going to discuss the stationary distribution, time dependent probabilities and so on. So, how to find the stationary distribution? Solve pi q is equal to 0, pi is the vector, consists of pi i's, where pi i's are nothing but what is the probability that n customers in the system, what is the probability that I customers in the system in a long run. So, that long run is defined in this way. The n of t is a stochastic process. As t tends to infinity, the number of customers in the system in a long run, that is going to be the n, and pi a is nothing but a probability that n I customers in the system in a longer run. So, now we are going to solve pi q is equal to 0 with the normalized equation summation of pi a is equal to 1. So, once you frame the equation, you will get a pi 1 in terms of pi naught and pi I minus 1 in terms of first pi I, then substitute recursively you will get in terms of pi naught. So, since it is a homogeneous equation, you will get all pi i's in terms of pi naught. So, use the normalizing equation summation of pi a is equal to 1, you will get pi naught. So, the pi naught is equal to 1 minus rho, where rho is lambda by mu. And since I am relating this stochastic process with the birth death process with the infinite capacity, if you recall, the stationary distribution exists as long as the denominator of a pi naught, that series converges. So, that will converge only if lambda by mu is less than 1. If lambda by mu is greater than or equal to 1, then that denominator diverges. Accordingly, you won't get the stationary distribution. So, to have a stationary distribution, you need rho has to be less than 1. That also you can intuitively say, whenever the system is stable, that is corresponding to rho is less than 1, in that you will have a stationary distribution. That means in a longer run, this is a proportion of the time the system will be empty. And the pi n is nothing but the n customers in the system in a longer run, that is 1 minus rho times rho power n, where rho is less than 1. This rho can be visualized as the offered load also, because the rho is nothing but the mean arrival rate and the mu is the mean service rate, and this ratio will give the offered load. And 1 minus pi naught, that is the probability that the system is non-empty, and that is nothing but the server utilization. Server utilization is nothing but what is the probability that the server is busy. The server will be busy as long as the system is non-empty. So, the rho is the server utilization that can be obtained from this formula, and in a longer run the server utilization is rho.